Your success in Chapter 9 is really going to depend upon how well you did in Chapter 8 in understanding the concepts of how to run a hypothesis test. Because in this chapter, we're introducing several more types of hypothesis tests, but we also have difficult decisions to make along the way. And the wording of the confidence intervals that we create is also going to be a little bit challenging. So I'm going to say fasten your seatbelts because we're in for a ride on this video. Here we go. We're going to be dealing with the difference in means or proportions from two populations instead of one. That is what sets this chapter apart. Now, your null hypothesis is always going to be that the means are equal to each other. mu1 equals mu2, the mean from each of our two populations. But we're going to have three different types of alternate hypothesis, depending on whether we have an not equal to, less than, or greater than type of comparison between our two population means. So here we go. Let's just look at the assumptions here. We're assuming that N1 and N2, our sample sizes or our samples, are taken from normally distributed populations. We want that. Also, suppose the samples are taken independently. The two populations are independent of each other, and we can't have a data value belonging to both populations. If the population standard deviations can be assumed to be equal, then we do something which we call pooling the standard deviations. Okay, so I've already stated these tests here. These assumptions right here, but let's talk about this pooling concept. When considering whether we're going to do a pooled t-test, it's important to watch out for outliers because the presence of outliers calls into question the normality assumption. Remember that anytime you're doing something involving t with smaller sample sizes, you need to test for normality. Even for large samples, outliers can sometimes unduly affect a pooled t-test because the sample standard deviations and means are not resistant to them. Now, we are not using the word pool here in terms of a swimming pool. We're talking about aggregating, like pooling our resources together. Let's say you're going out to lunch with some friends and you each just have a few bucks and you can't really afford something on your own, but if you pool your money together, then you're able to go in on a larger meal or a larger gift for someone. That's the type of pooling we're dealing with here. And when you're dealing with smaller sample sizes, where the sample standard deviation isn't that meaningful because it's just based upon a small number of data values, if we pool the two data sets together, then the standard deviation has a little bit more meaning. And that's what we're dealing with here. So anytime you run a two-sample t-test, which will be one of the tests we do in this population or in this chapter, you need to decide whether or not we're going to pool the standard deviations. And there will be two main reasons when you can do this. The first one is you are told that sigma 1 is equal to sigma 2. Notice that these are the population standard deviations that are assumed to be equal, not the sample standard deviations. Further, that you note that you do not even need to know what those population values are. You just need to know that those population standard deviations are assumed to be equal. So they will tell you that, or for some reason you will know that. However, more commonly, it's this second criterion that we rely upon for determining whether we're going to pool the standard deviations. Okay, when you know that the two populations were created through random assignment, then that will be a reason for pooling your standard deviations. And I want to make a comment here that this is not the same as random selection. Okay, now I'm going to call attention to a couple pictures here, and this is a concept that we talked about way back at the start of the course. When you are picking names out of a hat, That is random selecting. You are choosing names randomly. But when we're assigning subjects into a treatment group or into a control group, that is a random assignment. We're talking about this second one here, like when you want to put people into a control group versus a treatment group. You don't want to bias one group over the other by who you choose to be in which group. So when you choose them randomly, you're eliminating that bias, but you also can assume that the composition of the two populations is roughly the same. You don't have a reason for it not to be because of this random assignment. Okay, now students often like to ask whether the two populations were pre-existing before the experiment, in which case the standard deviations would not be pooled. Okay, so use non-pooled, the subjects are not randomly assigned. For example, let's say we have a population of men and a population of women. Those are two populations that are independent of each other. And we don't flip a coin to determine whether you're going to be a guy or whether you're going to be a girl. You already are one or the other. There's not a random assignment. So I usually say in that case, your condition, your gender, so to speak, is already pre-assigned or predetermined. And that is what tells you you will not be pooling the standard deviations in that case. This is a key concept that you want to get down, and we will be discussing it as we go through the various examples in this chapter. Okay, I want to make a note right off the bat here that if you haven't looked at the end of your set of lecture notes for this chapter, you actually have a flow chart that I've created that helps you to determine what type of test we will be doing on any given situation. Now, we already know about the one proportion z-test. That was in the previous chapter. Okay, we also know about the t-test. That was in the previous chapter. But the two proportion z-test, that's in this chapter. The two sample t-test, where you'll have to decide on pooling or not pooling, as well as something called the paired t-test, are all going to show up in this chapter now. And this is the thought process you want to go through. It's almost as if there's another branched decision at the beginning of the problem on the left here, where when you get a problem, you say, okay, am I dealing with proportions or means? If you're dealing with proportions, it's either the one proportion z or the two proportion z test. If you have means, you're then going to say, okay, do I have one sample mean or two sample means? Am I dealing with one population or two? And that will then take you on one branch or the other. If you know that you have two populations, you're going to ask, do I have paired data? More on that later. And if the answer is yes, you're going to do the paired t-test, which I'll teach you how to do later. And if the answer is no, you'll move on to the two sample t-test. So this is meant to be an indispensable tool here to help you organize your thoughts and help you to determine which type of hypothesis test you're going to do on a particular problem. As I've said before, the two main places that we make mistakes on this unit are, one, choosing the proper test to do on a particular problem. And then number two, once you've chosen the test, choosing the correct alternate hypothesis. Because if you've got the wrong inequality in the alternate hypothesis, that's actually going to lead you down the wrong path and give you wrong numbers and lead you to the wrong conclusion. Okay, let's dive into our first problem, and you can see that there's a whole lot of data to type in on this problem. So you might want to pause this video right now and just type in all these male patient data into list 1 and the female patients into list 2. So I'll wait here for you to pause and do this. Now, I am going to have a convention in these problems, and it doesn't have to be this way because If you get your populations reversed, it also causes problems in this chapter. So my convention is going to be, if they give me data in a particular order in a table, the first set of data will be my first population, and the second set of data will be my second population. If they don't give us the data in this format, then I go up into the paragraph, and whichever one is introduced first. Notice how men are introduced first and women second. That will be my way. That's just my convention on how to do it. You don't need to, but for consistency's sake, I'm going to do that throughout this class. So here we go. The U.S. National Center for Health Statistics compiles data on the length of stay by patients in short-term hospitals and publish its findings in this journal. Independent samples of 39 men and 35 female patients give the following data on the length of stay in days. Now, 2 comments. These are independent samples. They need to be because men and women are independent of each other. But notice that the sample sizes from each population do not need to be the same. Further, since our sample sizes are above 39 in size, each of them are above 30, we do not need to test for normality. If you go back to the central limit theorem, or even if you just go back to the table we looked at a moment ago, it says test normality assumption if n is under 30. So if our sample sizes are 39 and 35, we're good to go here. And I know that was the t-test we were looking at on that table or that flow chart, but it applies to the 2-sample t-test also. So, do the data provide sufficient evidence? That's the wording we're used to that signals, hey, we've got a hypothesis test coming. Do they provide sufficient evidence to conclude that on the average, the length of stay in short-term hospitals by males and females differ? Okay, now the word differ is a key word because it tells us we're going to be doing a not equal to in our alternate hypothesis. And they said, perform this at a 5% significance level. I've already got that typed in. Now we are comparing means. So I wrote mu subscript m for males and mu subscript f for females. And I said they're either equal or not equal to. Okay, pretty straightforward. And the males were my first list. Now you could just go mu1, mu2, and that's what your calculator is going to have. However, for us, I'm just going to go with subscripts that are a little bit more meaningful to me. It helps me to organize my work. Okay, now we go through our flow chart and we say, okay, we're dealing with means. Do we have 1 mean or 2? Obviously, we have 2. Is my data paired? Well, we don't even know about what this pairing thing is yet, so the answer is no. So now we move on to, okay, are we going, what test is it? And it's going to be the 2-sample t-test, but we have to decide, are we going to pool the standard deviations or not? And in this case, because we have men and women, okay, and they're already assigned to what their gender is, we're not randomly assigning them to a gender, then we're going to say this is going to be a non-pooled procedure. Now, when you go into your calculator, into the 2-sample t-test, let's take a quick look. I'm going to hit my stat button here. I'm going to go over to the tests. I'm going to go down to the 2-sample t-test, which is there at choice 4. And my data is going to be in my 2 lists, list 1 and 2. I'm going to need to go in here and say, okay, this was going to be a not equal to test. And notice on the next line, I've got the choice of pooling or not, yes or no. So we would highlight the word no on this problem before we move down to hit calculate. Now I'm not going to finish this problem because I've got a different set of data in my calculator. So let's go back now to our problem where I've already pre-worked this out, and come on, and take a look at what values you should be getting if you've paused this video and are checking this on your own, which I hope you're doing. And you should be getting these values right here. Once you got to this point, the rest is just the same as what we did in the last chapter. We look at that p-value, about 56%. We say, hey, that's way above alpha, which is 5%. So since P is greater than alpha, we are not going to reject the null hypothesis. And anytime we don't reject the null hypothesis, we know how to word our confidence interval. The data does not provide sufficient evidence that what? That the length of stays in short-term hospitals differs by gender. That's just what it was asking about right there. And here again, if you want to see it, is all the output that should have come out of your calculator. Now, let me just mention a little bit about what comes out of your calculator. We are used to looking at the T and the P, but we really didn't know what the mean was from either of these two lists because they were in the list. So it's kind of nice because it tells us the mean from list 1, that's our males. The mean from list 2, that's our females. So we know just looking at it, the men stayed in the hospital about 7.9 days compared to women who stayed in the hospital at about 7.1 days. And it did look like men stayed in the hospital a little bit longer. Now, was it far enough apart between these two for us to say that there was a difference that was significant or not? That's what we are going to find out in part B. So here we go. Determine a 95% confidence interval for the difference. All confidence intervals are for the difference between means or proportions. And your calculator is going to go mu1 minus mu2 in its calculations. So find this 95% confidence interval for the difference between the mean lengths of stay. Now, just off the top of our head, if I was looking at this and I said, okay, men, I'm rounding, it were 7.9 and women stayed 7.1 days, aren't those about 0.8 days apart roughly? Okay, that's just a rule of thumb, a little bit of a kind of a sense of what we're getting. Now, we said do not reject. We did not have enough evidence to suggest that this 0.8 days difference was going to be all that meaningful or that significant. So let's take a look at what happens on our calculator. I've actually, already done it. And I did a 2-sample T interval. Notice that matched the 2-sample T test we did earlier, and it's going to remain not pooled. And on my calculator, I'm going to get this interval right here. The rest of the information going down is the same, but what I want to call to your attention here is how 0.8 is right in the middle of that interval. Okay, if you go and subtract about 2.1, you're down, well, that's not 2.1, about 2.6 down or 2.6 up, you're going to see that that's roughly in the middle of the interval. And I rounded with that 0.8, but that's kind of the idea I wanted to share with you. Okay, let's move to the next example. This one's got other things that we have to pay attention to. So here we go. In a packing plant, a machine packs cartons with jars. A salesperson claims that the machine she is selling will pack faster. So to test that claim, the mean it takes each machine to pack 10 cartons are recorded, and the time is in seconds, and the result is in this table below. Now, for this problem, you actually have a choice. You can either type all these first 10 values into list 1 and the next 10 into list 2 to represent the new machine versus the present machine. Or because I've summarized the data, you can skip typing them in and you can just type in the summary statistics here. That's going to be your choice when it comes to typing this into the calculator. Now, in part A, do the data provide sufficient evidence to conclude that on the average, the new machine packs faster? Perform the required hypothesis test at a 5% significance level, and you can see down in step 2, I've already listed alpha as 0.05. Then it says, assume the population standard deviations are equal but unknown. In other words, sigma 1 equals sigma 2, the population standard deviations. And that right there, folks, is evidence that tells us that if this is a 2-sample t-test, we are going to be able to do it as a pooled procedure. Okay, so we go through trying to choose what type of test to do, and automatically we are going to say, okay, we have means. We have 2 populations because there's 2 different machines. They're independent of each other. And we're not pairing our data, which we don't know about yet. So again, it's our 2-sample t-test, and we've said that it's going to be a pooled test. So I've already got that listed right there. But let's take a look at our null hypotheses. We got a new machine and a present machine. And it says, do we have evidence that the new machine packs faster? Okay, these are the times in seconds. And when something packs faster, its time goes down. So I have the new machine and the old machine. And if the new machine packs faster, its time is less than the time of the old machine. And that's why that's a less than. Can you see how you've got to do some reading sometimes to interpret which inequality goes in that problem? Now, to make it even more interesting here, I had the new machine be the first population. Had I let the old machine be the first population, then instead of a less than, that would have been a greater than inequality. So I wanted to call that to your attention here because there's lots of little decisions that you need to make along the way. Okay, we're going into our calculator and we're going into our 2-sample t-test. Now I did this using the summary statistics right there. But if you didn't want to use the summary statistics in the bottom of this chart, you could have actually typed the raw values in, and then you would have hit the data at the top there. And then it would just say list 1, list 2 is where your data comes from. Now, I've also listed for you what should be coming out of this calculation. And so there's the values, and I've rewritten a little bit larger your t value and p value to emphasize them. And notice how our p value is a whole lot less than alpha. So since p is less than alpha, we're going to reject the null hypothesis. And since it's under 1%, the p-value that is, we're going to say the data strongly suggests that the new machine packs faster. Okay, so several things can go wrong here. First off, if you don't pool the standard deviations, you're going to have the wrong test chosen on your test. Now, sometimes pooling versus not pooling, the difference in the values of T and P aren't that far off, but they sometimes are off. It just depends upon the problem. Now, if you had the wrong inequality here, and you had a greater than, instead of 0.0015, you'd have 0.9985. You'd have the complement after subtracting from 1. So instead of having a strong rejection, you'd have a strong do not reject. Okay, the exact opposite response, all hinging on that inequality. That's why I said a little while ago, choosing the test and then choosing the alternate hypothesis really are your 2 key decisions and ones that we're going to want to get practice with. Okay, now let's continue on to part B, because in part B it says determine a 90% confidence interval for the difference between the mean time it takes the new machine to pack 10 cartons and the mean time it takes the present machine to pack 10 cartons. Okay, the difference between the means. In other words, how much faster is the new machine? Well, we did a 2-sample t test that was pooled earlier. So this is going to be a 2-sample t interval. Okay, that's pretty straightforward. So let's see what we're going to do. I plugged those into my calculator and out came those values that you see right there on the screen. So hopefully you can pause this video and double check that on your own. And let me see what I've said here. we can be 90% confident that the difference in times to pack the 10 cartons is between these two numbers. Something's going on here. The order of the numbers changed right here. This went from negative, oh, these were both negative, and I made these positive. Why is that the case? Well, I'm going to tell you, look at our confidence interval and both ends are negative. When both have the same sign, this top set of rules is going to take over. We can be blank % confident, there's my 90% confident, that the difference, the difference between, or in whatever context, what is it? What's my context? And the time to pack the 10 cartons, that's my context, is between this and this seconds. But then it says both values should be positive and in order from small to large. These were both negative. And if I change the signs from negative to positive, they're going to be out of order. So I need them to run like a number line in order from small to large. If you are going to meet a friend somewhere for lunch, you don't say, hey, I'll meet you sometime between 2 and 1. You say, I'll meet you between 1 and 2. The intervals that we describe always go from small to large. And because this is a difference, and I said, how much faster does this second of this new machine pack? You're never going to say, oh, it packs -1 seconds faster. That makes sense. Just like distance must always be positive, how much faster is that machine going to be is going to be a positive number of seconds also. And that's why we're switching this from a negative to a positive. Those are the rules that take over when both ends of the confidence interval have the same sign. Now I've got another comment here about why those are negative. Let's take a look over here. And I said, your calculator is taking those two mean times and it's subtracting. See up here, it's finding a confidence interval for the difference between the means. Now, our first mean was 42.13, and the second mean was larger. And when it goes mu1 minus mu2, when it goes small minus large, you're going to expect a larger answer of -1. Okay, and that's why -1 is right in the middle of that answer. We'd expect the new machine to pack about 1.1 seconds faster on the average. That would be a point estimate for the difference between the two packing speeds. You can see there's a lot to pay attention to here. Next problem. Researchers studying obesity wanted to compare the effectiveness of dieting with exercise to dieting without exercise. Okay, there's our two different treatments. 73 patients were randomly divided into two groups. Randomly divided. That is going to be key so that if we have a 2-sample t-test, that'll be a pooled procedure. And you really do want a random assignment here because you want to make sure that there's no bias involved. You want the composition of the two groups to be assumed to be about the same, which is what you get when you do a random assignment. Okay, group number 1, composed of 37 patients, was put on a program of dieting with exercise. And group number 2, composed of 36 patients, dieted only. Okay, the result for weight loss in pounds after 2 months are summarized below. So for group 1 that dieted and exercised, they lost about 16.8 pounds. Group 2 dieting only, they lost about 17.1 pounds on the average. But notice the standard deviation was a little bit larger. Okay, so part A, at the 5% significance level, determine whether there is a difference between the two treatments. In other words, is there a difference between the mean weight loss? So, okay, I have group 1 and group 2. So I'm going to go, instead of 1 and 2, I used EX for exercise and NO for no exercise. And is there a difference between the groups? I went with a not equal to. Okay, We are going to do a 2-sample t-test that is pooled. And again, the pooling is due to the random assignment into those categories, into those 2 populations. Again, if you want that on your flow chart that we saw earlier, okay, pooled if either you can assume sigma 1 equals sigma 2, or you know that the subjects or data were randomly assigned into the populations. Okay, so I've got it right there in that chart to help you with that memory clue. Okay, at that point, we go to our calculator, and you can see I've entered in the values right here that were up in that chart. I chose not equal to, and you can't see it because it's covered up, but there it is. I've highlighted the word yes for pooled, and out come these numbers that you see here, which I have rounded to 4 decimal places in my listing up there in the problem. Okay, now we look at this and we say, okay, P is 0.7727. That's way bigger than alpha. So since P is greater than alpha, do not reject HO. And we're right back to all that stuff we were doing in the previous chapter. And we can say the data does not provide sufficient evidence to suggest that there is a difference between the 2 treatments. And the wording that I've used right there for this is just the standard wording, okay? The data does not provide sufficient evidence. That's what we say when we do not reject. And the second half is the alternate hypothesis, which says there's no difference. Does not provide sufficient evidence to suggest there is a difference. When there is a difference, that means they're not equal to each other. Okay, part B. Determine a 90% confidence interval for the difference in mean weight loss between the 2 regimens and interpret our results. Difference between mean weights. Now, our confidence intervals for a difference. Okay, let's take a look here. When you do this on your calculator, and this will be a 2-sample t interval that was pooled, notice how the answer that you get here has one end of the confidence interval that's negative and the other that is positive. If you go back to the cheat sheet I gave you here, this is our boilerplate language for how we're going to word this conclusion. Okay, now I'm going to make several key points here. On the previous problem, when we worded our confidence interval, notice I underlined the word difference. We can be blank % confident that the difference is between here and here. The word difference is part of the different signs, but we don't use the word difference in our explanation over here at the right. That's one thing I want to call to your attention. We can be blank %. Well, that'll be 90% confident that either, and then I need the context without the population name. Okay, this is going to refer to the mean weight loss that we're dealing with. And I don't mention group 1, group 2, or dieting with or without exercising at that point. It's just what is the core part of what are we talking about here? Either this is, and it's going to be up to. Now notice both halves are going to begin with up to. And then we take the 2 numbers that we have here. I drop the negative. I change it to a positive. Both of these became positive. And I say up to this many pounds higher for one group or up to this many pounds higher for the other group. Now, how do I know which group is which? Well, I've told you that both values need to be positive. That's why my -2 turned into a +2, 0.025. And it says the negative endpoint, that's the -2, means that the mean or proportion of the second population is higher. My second population was the ones who dieted only, no exercise. So I wrote that right there. And then or up to 1.4247 pounds higher for those that dieted with exercise. Lots to pay attention to right in there. And I do need to have the words up to there. We're not saying that the difference is either this or that this is an interval between two numbers, up to this much on one end or up to this much on the other end. And that's why the words up to need to be in there. Now, I've been teaching this, 25 years, and it's only been the last year or so that I've actually given out this boilerplate language to help you to really construct these intervals. Now, you don't have to use this wording exactly as is, but for those of you who are fearful of trying to word these things and going rogue on your own, I provide them to you as a help. Okay, let's continue on here. Next problem. The following are ACT results for college-bound students broken down by gender. And you don't need to rush and type them in your calculator because I just have a summary here. And it says if you cannot assume the population standard deviation of test scores for males and females are equal, okay, we can't assume sigma 1 equals sigma 2. Does it appear that college-bound males are, on the average, outperforming college-bound females in the math portion of the ACT? Now, something I'm going to mention here, and I'm going to go, and I'm going to just write a little comment here, and I'm going to go, Is the data normally distributed? I wish they had asked this as part of the question, because when your sample sizes are each under 30, technically we need to check for normality. And if we don't have the means of checking for normality, such as in this case, because we don't have the raw data to type into our calculator and do a normal probability test, we're at least responsible for saying, we've got an issue here, so that whoever is looking at our results can go back and at least know there might have been an issue here and possibly call the results put it under scrutiny. Okay, so does it appear that college-bound males, I'll make that my first group, on the average are outperforming college-bound females? Okay, we've got two populations here, males and females. And if males are outperforming, that means they've got higher scores, and higher scores gives us a greater than. If you made females be population 1, note that the inequality would have been reversed. Because I don't know whether the standard deviations are population 1s are equal, and because people are not being randomly assigned into a gender, this is going to be a 2-sample t-test that is not pooled. And I've done this over here at the right on the calculator if you want to check all the results on your calculator, but basically it's a p-value of 0.0758. Now, since that p-value is bigger than alpha, do not reject HO, and the data does not provide sufficient evidence to suggest that males are outperforming females on, and I left it short there, but on the math portion of the ACT. Okay, now part B says, okay guys, same question, let's do it all over again, but this time we're going to change out the significance level to 10%. Now, when I do that, where's my cursor? There it is. All the steps of the hypothesis test are the same, except right there in green, you can see I changed my 5% to a 10%. Now my P is not smaller than alpha or bigger than alpha. P is smaller than alpha. So now everything is going to change. Okay. P is less than alpha, so we're going to reject HO, and the data seems to suggest that males are outperforming females. Notice how, and this is the reason for the problem here, notice how you get a different result based upon the significance level of the problem. I'm going to say, based on our p-value, okay, if I take that p-value, which is the same in both cases, 0.0758, if I subtract it from 1 to get 0.9342, okay, that means we are 93.42% confident that males are doing better. That's how much confident we are. However, up in the top half of the problem in part A, we wanted to be 95% confident. How do I know 95%? Well, there was a 5% significance. 1 minus that 5%, or 100% minus 5%, got us down to 95%. In part B, we changed this. When 10% is the significance level, that means there's a 90% confidence level. And so you can see that depending on how sure we want to be, it's going to change potentially what decision we draw or come to. And that's kind of the idea that I wanted to get here. And that's what sets this problem apart from the others. And that's an important realization. Okay, now we're going to change gears yet again. Now we're going to be talking about proportions, and I'm going to give you the assumptions here, but we're not going to check them. But just know that we can't deal with slim categories that we're not really expecting in many people. If our N1 times P1, our N1 times 1 minus P1, our N2 P2, or our N2 times 1 minus P2. If any of them are under 5, then we're in trouble, and we're not supposed to be running the test, even though the calculator is doing it for us. But again, I've told you I'm not going to emphasize this checking of assumptions. I'm just telling you about them as a formality. We are going to spend our time checking assumptions when we're dealing with t-tests and that normality assumption. Okay, here we're going to be pooling the proportions. Last time we talked about pooling the standard deviations. Here we're going to be pooling the proportions, and I've given you the formulas that we would be using if we were to be doing this manually, but we're not going to be doing these things manually. If we ever need to find the margin of error, I don't want to use that formula. I just want to find the confidence interval and find half of the width of that interval to determine what that margin of error is going to be. Now I have another rather old video or question here. In April and May back in 1985, the Gallup organization conducted a poll to estimate the percentage of Americans who approved of how President Reagan was handling his job. So you can see that in April, which is our first proportion, 795 out of 1,528 people said, yes, I approve. And that went up in May when you had 840 people out of 1,528. It did appear to go up. Notice the percentage went from 52% to almost 55%. Now, is that increase significant? That's what we're trying to find out. At the 5% significance level, do the data suggest that the percentage of those who approved of Reagan increased from April to May 1985? Well, we can see it increased, but can we say that at a 5% significance level? That's the question. So this time my populations are not people or men or women, it's 2 different months. Now a date or a survey can't take place in both April and May, so they are independent of each other. So I used A for April and M for May. And if it increased, now normally increased refers to a greater than, but if it goes up from April to May, that means the May is larger and the April is smaller. So don't just look at that word increased and say, ooh, it's going to be a greater than. This is actually a less than problem if you've got April as your first population. As I've said, you've got to be careful on this inequality. You do not want to rush through these. So on step number 3, we have to say, we're dealing with proportions and we've got 2 of them. I wonder what test it could be. It's going to be our 2 proportion z-test. Now on your calculator, when you go into that menu, pretty straightforward. It's going to ask you for x1, n1, x2, n2, and it's going to ask you, do you want to go with a less than, greater than? And I'm sure you can figure your way through. And I want you to verify that you can get these numbers that I have here, which I've actually summarized here by rounding to 4 decimal places. And our p-value, look how close it is to 5%. It's almost significant at the 5% level, but not enough. Our p is bigger than alpha. So since p is greater than alpha, do not reject HO. So the data does not provide sufficient evidence, or I'm going to say the data does not quite, it's almost there, and I'm editorializing here, the data does not quite provide sufficient evidence to suggest that his approval rating increased between April and May 1985. It was a close call. We're almost 95% confident. We're actually 94.87% confident. We just missed it by that much, as Don Knotts would have said back in Get Smart, or Inspector Gadget, as you might know him, or his character, I should say. Okay, here we go on to part B. Construct and interpret a 90% confidence interval for the differing percentage between those 2 months back in 1985. Well, we did a 2 proportion Z test earlier, so we're going to do a 2 proportion Z interval. Now, I wanted to call to your attention that when you did it this time, first off, we get a negative on one end and a positive on the other end of the confidence interval. But notice how this went into scientific notation. That really stands for 2.18 times 10 raised to the negative 4th power, which means move the decimal 4 places to the left. Now, don't accidentally slip an extra 0 in there. You're moving it 1 place to go past the 2, and then you're putting 3 zeros in so you can jump over those 3. So you want 3 zeros before the 2, and if you're rounding to 4 places, that would be 0.0002 that you would list out on the p-value. Okay, so that is our interval, and since the n's were different signs, I'm rewriting our little cheat sheet on how we're going to go through and describe this, because our answer can really go either way. We don't have enough evidence to say, hey, his popularity did increase, at least with this level of confidence. So here we go. We can be blank % confident. We can be 90% confident that either, what's my context? It's the proportion of those who've approved of Reagan, that's really what the problem was about, is, I changed it to was because that's the past tense there, and here's my up to, and here are my 2 numbers, okay, and both of them say, they're both positive, both of them are in terms of percentages, which means I've moved the decimal places over 2 more places. And then I said, when it's negative on that endpoint, okay, the negative endpoint means that the proportion of the second population is higher. The second population was the month of May. That's why I have higher in May for that first number and higher during April for that second number. We knew it was leaning towards being higher in May, and so that larger percentage going along with higher in May just only makes sense there. And we knew it was just a borderline chance that it actually went down, which means there's 0.0218% chance that it was higher back in, or that percentage higher back in April. Not percentage chance, but percent popularity rate. Okay, let's continue on here. The Organization for Economic Cooperation and Development summarizes data on labor force participation rates. Independent samples were taken of 300 US women, and 250 Canadian women. Okay, US and Canadian, 2 separate independent countries. Of the US women, 211 were found to be in the labor force. In other words, they were working. And of the Canadian women, 170 were found to be in the labor force. Okay, so we've got this many out of that many. We're given the X out of N for each population. At the 5% significance level, do the data suggest that there is a difference, there's our key word, between the labor force participation rates. Okay, so difference, I'm going to underline that because that tells us that we're going to have a not equal to inequality. And my subscripts are going to be P subscript US. They don't look like subscripts, but I'm meaning for them to be. The proportion for the US is either equal to the Canadian or not equal to the Canadian labor rate for the women. There's my 5% significance level. We know that this is going to be a 2 proportion z-test. And let's take a look at what we're entering into the calculator. Now, I had the US women going first, so you can see it was requesting my X1 and my N1, my X2 and my N2. They wanted the not equal to, and then I hit calculate. And here are the values that came out of my screen, as well as the rounded versions there. And you can see that our p-value of 0.5548 is much larger than alpha, and therefore we will not be rejecting HO. And so the data does not provide sufficient evidence to suggest a difference in the labor participation rates. Okay, once you know the format of these types of problems, they're really not that bad. It's the 2 sample t-tests that were a little more challenging. It's the interpretation sometimes of the confidence intervals where we have the tough spots, and that's what we're moving on to in this next part. So it says, find and interpret a 95% confidence interval for the difference between the labor force participation rates. Oh no, I hate it when there's our do not reject, because that means we're probably going to have the split conclusion over here. If there is a reject and we have a definitive conclusion up above, that usually makes the wording of our confidence intervals a whole lot nicer. So we did a 2 proportion z test up above. This is going to be a 2 proportion z interval. And just like I told you, one end is negative, the other end is positive on this confidence interval. And so that tells us we've got to look at this wording carefully in how we go about writing this interpretation of this confidence interval. We can be 95% confident that either, now what is my context? The labor participation rates. Now it says without the population names. I'm not mentioning the labor participation rates of the US and Canada, just the labor participation rates. Are, that's a form of the verb is or to be. Are, and then I've got these 2 options, either up to, and I took my first decimal number, I took off the negative, I made it positive. I also moved the decimal 2 places to the right, so we could look at that as 5.42% higher for. And then it says when it was the negative endpoint, it's the second population that was higher. The second population was the Canadian woman, and that's why I have Canadian women there. Or, and then I took my other number up to 10.089% higher for the American woman. Okay, so hopefully that little cheat sheet helps you to get all those details correct in this interpretation of this confidence interval. Now we're going to learn a whole new type of test, and we've got all sorts of extra details to work on in this problem. Before we get to this problem though, let's start with this summary, because now we're getting into these paired samples. Okay, and with paired samples, we are not dealing with independent populations like we have been already in this chapter. Men and women were independent of each other. Canadian women, US women, independent of each other. Now there is a dependence between the 2. Suppose you wish to examine the mean value of a population before and after some stimulus causes a change. Since the samples are chosen from the same population before or after this stimulus, they aren't necessarily independent. your calculator does not have a built-in feature where you can just go to the paired t-test. So we're going to have to fake out or trick our calculator when we go to actually do these problems. And I'm going to teach you how to do that right now. So here's our first of two major examples. The Nielsen Company collects data on the TV viewing habits of Americans. 20 married couples are randomly selected. Their weekly viewing times in hours are shown in the table, and I've got that written at the left because that's where I could fit in that large table on the screen. Okay, at the 1% significance level, does it appear that married men watch less TV on the average than married women? Or part B, does it appear that married men watch less TV on average than their wives? Okay, I really think this problem really should be about married men and their wives because that's where the pairing occurs. However, in a previous edition of another book that I used, they actually talked about married men and married women, and in that case, it drops the pairing. See, it's kind of a weird thing. When you're comparing men and their wives, there's a connection. But in our class, we've got some married men, we've got some married women, but they're not married to each other. There's no necessarily a connection between those two groups unless they're being paired up. So I wanted to put that into this problem as two separate parts to show you we've got to be careful, one, with the wording, but also I wanted to show you how you handle each of these separately. Okay, so my population are husbands and wives, and I'm assuming that you have typed these two lists into your calculator as I have. And let's do the married men and married women first, okay? Married men, married women. I'm going to say, well, I've got husbands and wives here. I probably should change this to, actually, let me see this one over here. You know what? I uncovered the wrong one. My bad. Married men and married women. My arrow even told me, let's go that way. So mean of the men equals the mean of the women. And then does it appear that married men watch less TV for the men? That's why I have a less than there. And that's consistent with what we know. And it said, do this at a 1% significance level. And as I've told you here, when we talk about married men and married women, we're not necessarily saying there's a pairing between the two. Basically, what we're doing is we're saying, oh, we've got all these married men, and unfortunately it's called husbands, but here's list 1 and here's list 2, and we're just comparing the means of both lists. That's the idea here. And in that case, this is just a 2-sample t-test, and it's not pooled because men and women, we don't flip a coin to say, are you a man or a woman? There's no random assignment there. And so that would be a non-pooled problem. And this is what we've already done a couple sections ago at the first portion of this video. And you know how to do this already. And you know that when you do this on a 2-sample t-test, not pooled, out pop these numbers. And our p-value, you can see, is greater than alpha. And we're going to say, do not reject HO. And as a result, we're going to say the data does not provide sufficient evidence to suggest that married men watch less TV than married women do on the average. Okay, that's what you're familiar with. We've done that before. But now let's move into part B, because when we're talking about men and their wives, now there's a pairing between the two. Okay, this husband goes with that wife, this husband goes with that wife, etc., going down the list. And the idea is, you know, they got married, so they probably have similar interests. They both like to watch TV together, and maybe that causes a relation, you know, something, or maybe they both are outdoor people and they don't watch a lot of TV, and there is a reason for that. Okay, so that's kind of the idea behind this problem. So this time I'm going to not use M's and W's as you started to see. I'm going to use H and W for husband and wife, and this time it's married men or husbands watch less TV than their wives. So there's my subscripts. I'm still doing this at a 1% significance level, but this is going to be a paired t-test. Okay, now I've got to teach you how to do this. First off, you're going to go in and enter those values into your calculator. I've already done it on my calculator here, and I'm going to show you live what I did. So going into my stat edit screen, all those husbands and wives data is right here in column 1 and column 2. I'm going to move my cursor to the top of list 3. And while the cursor is up in that top position, I'm going to hit second L1 minus second L2. Now down in the bottom left corner of my screen, you can see list 1 minus list 2. Now, when you do something up in the top position, it says this is going to be applied to the entire column. So when I hit enter, it fills in all those differences going down. So for the paired t-test, you take your two lists, enter them in, you go up to the top of L3, you move your cursor into that top position and go L1 minus L2 to get those differences. Otherwise, you've got to do all that subtraction from left to right on your own. Then you're going to go do a t-test on list 3. So I'm going to hit my stat button. I'm going to go over to tests. I'm going to go down to t-test. Now my calculator doesn't know we're doing a paired t-test. It just thinks we're doing a t-test. But because I tell it list 3, then my differences being in list 3 is what makes this a paired t-test. Notice how I use mu sub 0 equals 0. That is a requirement here for the paired t-test. And I've got, well, I don't have it yet, but I would go down and I would select the less than, whoops, up to there, move to the right, select it. And then I would go through, hit calculate, and we'd be good to go. So let's go back to this other screen and make a couple of comments. I told you that we are going to go into our calculator and highlight these different things. It will always, when you do a paired t-test, you will do a t-test. It will be a t-test that's on list 3, and you will always use mu 0 equals 0. Now let me explain why we use mu 0 equals 0. Now, some of you don't need the explanation. It's just yeah, because you said so. But let's talk about what our null hypothesis is. We are saying the two of these are the same when we have the equal to. And when they are the same, we're saying there is no difference. That's what it means to be the same. And if there is no difference and list 3 contains the differences, we're expecting those differences to be 0 on the average. So that's the reason why we always use mu 0 equals 0. Now let me go all the way back to the flow chart. Actually, I have it up here a couple slides from now. In our flow chart, notice when it says on the paired t-test, there's the rules. Perform a t-test on L3, which is the same as L1 minus L2. Always use mu 0 equals 0 within that t-test. So it's part of the descriptions I've given you. How do you know when you're going to pair the data? You either have matched people or items, or it's a before or after type of model, because when it's before and after, it's the same people before and after some stimulus causes a change. So let's go back to our problem here now. And we've done this on our calculator. When you hit enter, out comes this conclusion, which I've summarized right here. And bada bing, we've got a result. This time, we're going to say, since P is less than alpha, this is under 1%, then we can say the data strongly suggests that married men watch less TV on the average than their wives. Okay, so a lot of details go into that paired T test. It doesn't take super long. It's just this first time that I showed you through, it takes longer to go through the first time. Now let's talk about the way we would word the confidence intervals, but I've put a little bit of a twist on this. I've always said, find and interpret this confidence interval, and I've given you the question. I'm asking you, in addition to finding it, how might you word the confidence interval for this question, for each part, and then find a 98% confidence interval for each interpretation. A little bit of a different skill. Okay, here we go. First one, find and interpret a 98% confidence interval for the difference between what? Between the mean number of hours TV watched by married men and married women. Two separate groups that we were dealing with. The second time, find and interpret a 98% confidence interval for the difference between the mean number of hours of TV watched by married men and their wives. But notice both times it's a confidence interval for the difference. If I go to look at that little chart that we had for the these problems here, the word difference here is underlined, but it's really, well, that's not really a good sign. Basically, you're anytime you are wording the confidence interval question, the word difference needs to be in there because it's really a confidence interval for mu1 minus mu2. Okay, so in the first case, previously we had done a two sample T interval, so a T test that was pooled. So here's the one that's not pooled. This second time, we just did the paired T test. Now we're going to do a paired T interval using all those differences that are in list 3, and out come these values that you see here. Okay, so it's pretty straightforward. You're going to do the matching interval that goes with the hypothesis test that we did. Now on this first one in part A, notice how it goes from a negative to a positive. So you're going to have this little cheat sheet that says, both ends have different signs to be able to interpret what this is. And on the second one, notice that both ends of the interval have the same sign, and so we will use the other cheat sheet to generate these. Now I'm going to ask you, please pause the video and try to use those two boilerplate languages to generate the wording on your own. See if I've done a good job of explaining this or not, or whether you understand the concept, and then come back in just a second when I explain it through. Okay, for this first one, you know we're going to say we can be 95% confident that either the, and I need some context, the mean TV viewing time. That's kind of what we're dealing. The mean number of hours of TV watched would be another way we could word that. Okay, is up to, okay, here we go. There's the first number, 13.3 hours higher for women, which was our second group, or 2.4978 hours higher for men, which was our first group. Now the second one here, we can be 95% confident that the difference, I'm going to have that word difference in there, between the mean TV viewing times for husbands and wives is between, there you go, these two different hours. Notice I made them both positive and I switched them to go from small to large. Lots of little details that you need to pay attention to in this chapter. Okay, let's go. One more example of a paired T problem. A pediatrician measured the blood cholesterol levels of her young patients. She found that many of them had levels over 200 milligrams per 100 milliliters indicating an increased risk of artery disease. 10 such patients were randomly selected to take part in a nutritional program designed to lower their blood cholesterol. 2 months after the program started, the pediatrician measured the blood cholesterol levels of the 10 patients again, and here's the data. Notice how we have 10 patients, and here's patient number 1 before and after. These are paired together because they're with the same patient. Now, we're not going to enter the patient numbers into our calculator because those are just labels. We're just going to enter the before into list 1 and the after into list 2. And I encourage you to do so right now. The question then asks, do the data provide sufficient evidence, or do the data suggest that the nutritional program is, on the average, effective in reducing it from before to after the cholesterol levels? And it says to do this at a 5% significance level. Now, I'm noticing here they did not tell us that the data was normally distributed in each population. So I'm just going to make that mental note with you right now that, oopsie, that's something we need to be aware of as we do this. Okay, we had a before and after. So I'm using mu before and mu after, and I used a B and an A. And notice it talked about effective in reducing. Reducing makes you think of a less than. But if the cholesterol level is going down, doesn't that mean it was higher before and it's lower after? That's some of the logic you got to have here in determining that this was a greater than. Okay, before needed to be higher if there's a reduction. Now let's just mention that this is going to be done at a 5% significance level. We've mentioned that this is going to be a paired t-test. So on my calculator, I'm going to go over to the top of list 3. I'm going to fill in the differences. I'm going to go L1 minus L2 like we did on the last problem. And I'm going to run a t-test on L3 with mu 0 equals 0. And here are the values that you get. And I've got them a little bit larger right here where we want it. And our p-value is just about 2%, which is under 5%. So since our p is less than alpha, we're going to reject the null hypothesis. And since we've rejected the null hypothesis, here we go. Our data seems to suggest that the nutritional program is effective in reducing cholesterol levels. Now, I threw another whammy here at you, and when you look at parts B and C, both B and C are asking you to deal with confidence intervals. The first one is for the difference between the mean cholesterol levels of the patients before and after the program. And the other one talks about the mean drop. Because we're dealing with a mean drop, that's the one that's going to involve the pairing. Okay, whereas the mean cholesterol levels before and after, that just says compare the mean of the before group and the mean of the after group, and we're going to use a 2-sample t interval, although technically that's not the right way to go because the 2-sample t interval requires that your two populations are independent of each other, and we know that these are not independent of each other because we know where the data came from. So a lot to pay attention to, but even then, the mean difference between the mean cholesterol levels of the patients before and the mean after tells us that we're dealing with a 2-sample t interval, not pooled, because we're not flipping a coin saying if it's before or after. It already is one of those two states. And I'm just going to give you the interval that should have come out of your calculator. How do you interpret it? Well, that's one of those split conclusions that's going to have to be using that boilerplate language. And I'm going to ask you to maybe pause the video and try and write that yourself. When you do that, you end up getting, we can be 90% confident that here's my context, the mean cholesterol level is either up to, and notice I changed the negative to a positive, there was my units, higher after the nutritional program, and the key word was after because that was my second population, or here's my other number, higher before the before. So keywords here were before and after, which I probably should have underlined there for emphasis. And again, I do need the up to here because it's an interval. Our values are going to range between these two extremes. Now for part C, we've said that this is going to be a paired t-interval using list 3. And because we rejected up above when we did the paired t-test, we've got a much more conclusive interval down here, and we're not going to have a split explanation with either this or that. And so bottom line, what do we have here? We're going to be saying here that we can be 90% confident that the mean FROP, I think you know that that was supposed to be drop in cholesterol levels, is between 0.7301 and 5.2699 milligrams per 100 milliliter due to the nutritional program. Okay, so we've looked at a whole lot in this chapter, and it is pretty challenging. And I do want to remind you that at the end of this set of lecture notes on the last page, you do have all these cheat sheets that help you through this unit. I've got these decisions here that you probably pretty much have this memorized, I'm hoping at this point, from the previous chapter, but it was still in play on this chapter. And here was our flow chart to help you choose the tests. And again, we have listed for you how you're going to word these different confidence intervals. So at this point, we kind of conclude this unit, but you probably want more practice with more examples. And that's where the homework comes into play and some of the other things we're going to do with these problems.